Dear students, I would like to repeat something from last lesson. So, in fact, it was the first lesson with me. So, I would like to make again this example. We can call it forced fall of particle. Forced. Why forced? Because there is an initial velocity v0 at the beginning of the process. So, we throw up the particle of mass m with velocity v0. Okay, and after that we will observe and investigate what is the process, dynamical process. So initial position of this particle is m. So we can write some given quantities. So it's m, it's a mass of particle, age, initial position, and v0 its initial velocity. We can calculate, for example, what is the course of velocity in time. So it's velocity in time. What is displacement in time? And a bit more we will see. So first step is usually to draw so-called free body diagram. But before this, it's very usual to set the coordinate system. This is a one-dimensional problem, so it's enough to set only one axis for this. So let's say that we propose this coordinate system with 0 here at the ground and upwards with growing positive values. So free body diagram will look like this. So we draw the particle at general position somewhere in the space. So general position in general position. So anywhere in the space. And we would like to draw all forces acting to this particle. So naturally, because we are in gravity field, so this is gravity force heading downwards. And second, it is an inertia force, so-called D'Alembert force. And the definition of D'Alembert force is that D is minus m by a. So the direction of this force is against positive values of acceleration. Positive values of acceleration are measured in the same direction as positive values of displacement, velocity, and acceleration, so upwards. So D'Alembert force, respecting this definition, must go downwards. So where is D? D'Alembert force. So free body diagram is very simple and is finished now. So we can write, let's say, general equation of dynamic equilibrium. So we know that sum of all forces plus D'Alembert force is equal to 0. So this is a very general equation of dynamic equilibrium, force equilibrium. So regarding our reality, we can write that all forces is in our case only G plus D is equal to 0. So this is a vector equation of dynamic equilibrium respecting our case. After that, we can split this vector equation into scalar form, and we get as many scalar equations as many dimensions we have. And as I said, this is one dimension case, so we get only one scalar equation where we can write D plus G is equal 0. We can add so-called force specification, where we specify D'Alembert force, the value size is m by a, and gravity force is m by g, and we substitute it back to this force equation. So after substitution we get m by a plus m by g is equal to 0, and we can cancel mass of the particle, and we find that acceleration of this particle is minus g. Why minus? Because we set the orientation of coordinate system upwards and the gravity acceleration heads downwards. So now we can step to calculation of kinematic quantities of the particle of the process. So first we can calculate velocity of the particle. We use a definition that acceleration is derivative of velocity with respect to time, and we can notice that acceleration we got already from previous calculation, so dv over dt is equal minus g. We can make a separation of values, so by multiplying by dt, and we get dv is equal minus g dt. And after that we can integrate equations. G, we can put out g out of the integration because it is constant, and we must add limits for these integration signs. So when time was 0, velocity was v0. So it's from v0, and we leave upper limits open. It means that upper limits are not constants but general values. So when we have a time equal to general time, so velocity is equal to general value of velocity in some time, so it's instant value of velocity. So we can continue here, and we can make this integration. So it is vt minus v0 is equal minus gt, and after some rewriting we get this. So it's a final formula for expression of velocity of in time of particle. Okay, So second, we can step to calculation of displacement. We use a definition that velocity is equal to derivative of displacement with respect to time. And we can use this part of equation and put it equal to the result of our previous calculation, because it's a velocity. So we add this. So continuing, after separation of variables, we can write dx is equal v0 minus gt by dt. So we multiplied both sides of equation by dt. So now we can put here and here integration signs, and also we must add integration limits. So when time was 0, the initial position was h, distance h from 0. So there is h, and upper limits will be made up by open values of t and xt. So left side after integration is this, and right side is v0 by t minus a half gt square. So we can calculate displacement in time, so it's h plus v0t minus a half of gt square. Okay, so this is a formula expressing the displacement of a particle in time. Now we can draw graphs of these functions. So first we can draw a graph of acceleration, second we can draw a graph of velocity, and finally we can draw a graph of displacement. Acceleration in time, velocity in time, and displacement in time. Concerning the acceleration, the value of acceleration is constant through all the process and is equal to minus g. Regarding the velocity, we have a function that velocity in time is equal to v0 minus gt. So we start at initial value of velocity, which is positive, and with increasing time is going down, and it is linear function. And finally, for displacement we start from h, because when t is 0, this term is 0 and this term is 0 as well. So x at 0 is equal h. So we start at h as an initial value of displacement. And because the relationships of these curves are integrational or derivative relationships, so when there is some function equal 0, so x, what is the integration, must be at maximum value or extreme, but in this case it is maximum. Okay, so and it's polynomial of second degree. So, and this is highest value of displacement, so this is x max. Now, tracking this process, we can say that at initial position h, the particle has initial velocity v0 and is going upwards with decreasing velocity, and we reach a point of culmination, so it is a maximum distance from the ground where velocity is 0, and after that the particle is coming back with decreasing size of velocity, but this velocity has an opposite direction, downwards. Okay, and now particle drops down. So this is explanation and tracking of this process, which was displayed in graphs. And if we consider the velocity of drop down, and we would like to calculate it, so how we can do it? So what is Vd as when particle drops down? Okay, so we can calculate it in two ways. We have system of two equations. First equation is an equation for velocity, so Vt is equal v0 minus gt, and second equation is xt is equal h plus v0t minus a half of gt square. For this moment of dropping down, we have some condition. We express it mathematically like this. So mathematical condition is that displacement at time when it drops down is 0, and velocity at time when it drops down is Vd. Okay, so we can substitute these conditions into this system of two equations. So we can write second equation as a Vd is equal to v0 minus gtd, and third equation 0 is equal to h plus v0 td minus a half of gt d square. So this is a very simple system of two equations with two unknowns. Two unknowns are td and vd, so we can simply calculate this, but it's more secondary school problem, and I will show you a more advanced approach how to calculate it more effectively. So we can start from the definition. So I hope you agree with this, that acceleration is a derivative of velocity with respect to time. Okay, I think everybody knows this. And we can expand this equation by 1, by number 1, and we can write number 1, for example, in this form. So this is 1. And after that we can swap these denominators, so we can rewrite it in this form. So this is dv over dx, and there remains dx, and we change this denominator. And what is this? It is velocity again. It is derivative of displacement with respect to time. So it is v again. So we can write finally that a acceleration is v by dv over dx. And this is a new form of this definition. We can use this definition for further calculation because we know acceleration. So v dv over dt is equal minus g. We can separate variables multiplied by dt, and we get v dv is equal minus g So we can write that v dv over dx is minus g, and we can separate variables, so we can multiply it by dx, and we get v dv is equal minus g dx. We can add integration signs and integration limits. Integration limit for displacement at the beginning of the process is that the displacement was h, and x is open value, general instant value of displacement. And when displacement was h at the start of the process, velocity was v0, and general instant value of velocity at upper limit is vx. Now we can continue with integration. So we can integrate v as a half of v square in limits v0 vx. It is equal minus g x minus h. So here we have a half of vx square minus v0 square is equal minus g x minus h. After calculation of vx, we can write that it is v0 square minus 2g x minus h square root plus minus. So what is the velocity of drop down, of touching the ground? So when x is equal 0, and we can substitute here, so vd is plus minus square root of v0 square 2g, and there would be minus h only, so we can write h and plus. Okay, so it's done, and this is a velocity when particle reach ground, and which sign we should take, because the orientation of coordinate system is upwards, so naturally the velocity of dropping down is negative, has negative sign. Okay, so this is vd, so we get this value